Let's add some specific details about the impacts of climate change or warming on the Arctic, Greenland and Antarctica. This is a paper that just came out literally this today. Today is Wednesday, so it'll actually come out tomorrow in Nature Communications. It is model projections including some historic periods. So the team takes the precipitation and snowfall from various satellite-based products and reanalysis. Remember, we talked about reanalysis products which blend data and models, and looks at the confidence in the models, CMIP5 and CMIP6 models, in reproducing the historic period, and then looks at their projections. So we are looking here at CMIP6 and CMIP5, and we are looking at seasonal snowfall ratios. So December, January, February, March, April, May, June, July, August, and September, October, November. Time evolution of snowfall ratios. The snowfall ratio over time, horizontal lines denote the transition from snow to rain dominated precipitation at point 5 from a CMIP 6 and CMIP 5, so showing these different seasonalities. The shading indicates 5th and 95th percent model spread for each, and all data are averaged as a 10-year rolling mean. So you make a 10-year running mean, so you don't see the year-to-year or interannual variabilities smoothed out. So as you expect, December, January, February has high amounts of snow compared to precipitation, so the ratios are way above 0.5 into 2100. But the alarming thing, of course, is that the newer models, which are better in many ways, resolution, processes, details, etc., predict that the ratio is beginning to drop quite soon in the next decade or so. And surprisingly, for March, April, May, this is slightly less alarming than in December, January, February. So it depends on a combination of warming, humidity, and snowfall versus rainfall in terms of processes. Arctic is a complicated place. In June, July, August, boreal summer, you expect that there is going to be a lot of rain compared to snow, so the ratios are well below 0.5. But this is the most alarming thing here, that compared to CMIP 5 models, CMIP 6 models seem to say that the transition from snow dominated rainfall in the fall months is going to transition to rain dominated precipitation much earlier. So this is around 2075 and beyond, and this is well into the 2060s. So at least a decade ahead of time, and you can see the ratio begins to drop off already in the current decade of 2020s. And evidence suggests that this is already happening. So you can see the historical period here. Already some changes are happening. So this is the Arctic specific problem, where sea ice does need a lot of cold temperatures which correspond to snow. Precipitation would mean a lot of warming, polar amplification we already talked about. The other specific issue for glaciers in specifically are these sorts of things, where you are looking at schematic section across an idealized ice sheet. So you are just looking at this horizontal axis representing the distance in kilometers from the left margin here. Vertical axis represents elevation about above the flat base. So we are not complicating with topography here. What are the key aspects? If you look at the accumulation, so you are going away from the left margin, you can see that there is a peak of the glacier, and the glacier flows in both directions. So when you are moving in this direction, there is mostly accumulation here. Let's say you're going from the coast of Antarctica or Greenland towards the inland. So you have some melting happening below this equilibrium line. Equilibrium line is essentially where the ablation and accretion of the glaciers are equal to each other. That means there is essentially as much melting happening as a glacier flow and accumulation happening. If you go above that, then there is snowfall and there is net accumulation. So when people drill cores, they have to pick places which have kept the signal over however many years you want to hope to get. In Antarctica, for example, we have now time series of ice cores going back 800,000 years. So you want to pick a place that is at the peak like this, where you have proper recording of the information and the ice is not flowing. Remember, glacier has a rheology, it's compressed snow, it's not like brittle ice, so it flows. So the equilibrium line, what happens with warming? You expect the equilibrium line to rise, which means glaciers retreat. So the place where accretion and ablation are equal begins to move up. That's the very common outcome of warming, right? So you see what happens here. As the equilibrium line moves up, here you begin to have more and more loss or ablation of ice. So the glacier retreats, as you can see, and equilibrium line is now here. So here there is more ablation, here there is more accumulation, but the region with accumulation has shrunk. This is what you are going to face, already facing over Greenland and Antarctica. I hope it's clear. Please read the book to make sure you understood. There is also the hysteresis effect in glaciers. Many components of the Earth system have a hysteresis effect, which means we already kind of implied it in the melting phase and the accumulation phase of glaciers. So here we are looking at the equilibrium height of the equilibrium line and ice volume, and depending on whether you are at a situation where there is no ice. So if you go back about 34 million years ago, Greenland and Antarctica didn't have any glaciers. So let's say orbital forcing started to build glaciers. So ice volume will increase and equilibrium line will obviously move up as the cooling happens. And once you've acquired a certain ice volume, if orbital forcing or human activities begin to warm, then the so you have reached, let's say, a new equilibrium line here, and as warming happens and ice volume begins to decrease, the ice volume doesn't decrease the same as it built up here, because there is inertia in the system and the equilibrium line begins to behave this way. So you increase the height of the equilibrium line, and the ablation zone and the accumulation zone begin to move, and the equilibrium line of course moves, and the ice volume decreases. So the build-up phase, for example, going from here to there versus going from there to there, they are not symmetric. Okay, so that's the hysteresis. That's what we implied in the ice albedo feedback as well. Okay, so whether you are going in this direction or you are losing ice volume, the processes are very different. You can read up about hysteresis. There are many good examples of how the pathways from A to B and B to A are not symmetric in systems which have hysteresis. So this shows the equilibrium line and ice volume of Antarctica and Greenland, it is negative. We will see in a minute that majority of the glaciers in Antarctica are below sea level. This creates really unique problems for Antarctica as well compared to Greenland. In Greenland, we say obviously it is above sea level, and we have other issues like the Mulan and so on and so forth. In many of the projected CMIP 6 and CMIP 5 simulation projected futures, Greenland here is fully glaciated and mostly deglaciated. So there are scenarios of emissions for the future where the runaway melting of Greenland does occur. You can look up this paper if you wish, and you can see how just tiny bits of glaciers would be left in this runaway glacier loss scenario. And this is not so surprising, because in the medieval warming, when the Vikings colonized parts of Greenland and they could do agriculture, and then the Little Ice Age came in, medieval warming ended, then they went extinct because the glaciers extended further. So the ice albedo feedback kicked in, but then since Industrial Revolution, we are beginning to accelerate the melting of the glacier as well. So in the case where you have extensive shelf ice like in Antarctica, there is something called the grounding line, where behind it you have the glacier that's sitting on land, whereas ahead of it the glacier has flown onto the water and it's floating. And this is the complicated part, where warming ocean can begin to make the glacier mass decrease because there is warming below, and the warm ocean can also increase water vapor content of the atmosphere and create snowfall over some parts. So Antarctica is facing these kinds of complex situations. So if you look at the figure again with a little bit more detail, so here we have, let's say, the grounding line that is retreating because with global warming, warmer ocean accelerated carving of the icebergs, which means the floating shelf begins to break into pieces because warmer water is beginning to inundate. So this is the circumpolar deep water intrusion that is increasing, and loss of ice is increasing as well, which means the grounding line, the line behind which glacier should exist on ground, is beginning to retreat because the warm water is beginning to drill into the glacier that's grounded here, which means the resistive stresses are beginning to do their work. So inland deepening of the seafloor here. So this is the counter gradient here. So this can be a runaway loss. So there is driving stress here because the glacier is flowing down the slope onto the ocean, whereas because the slope is downward here, there are resistive stresses for glacier retreat. But here this process of warm waters carving away or melting away the ice glacier is beginning to push the grounding line backwards, and this can have a runaway effect where the grounding line can just begin to accelerate in its retreat. So this is the Antarctic ice sheet vulnerabilities, and you can see here the projections for 2.6 in terms of ice thickness, and you can see that the thickness here is looking healthy in terms of the elevation above ground, this kind of accumulation and glacier thickness, glacier height. Here in RCP 8.5 you can see that large parts of these tall glaciers with good ice thickness are going to basically disappear, and it's going to thin like crazy. Many places are now less than a kilometer and down to 500 meters, and large part of this is going to just disappear. So all this is basically gone in the RCP 8.5 for 2500. So make sure you look at the time scale here. Okay, so this is the hysteresis part. So it is taken a long time to build, literally millions of years, and this is the retreat phase, which can come fairly rapidly. So this does matter. This is another figure showing retreating ground line flux at the ground line, isostatic rebound. We talked about the isostatic and eustatic. So the glacier loss is going to create eustatic sea level rise across the globe, whereas the subsidence and ascent of the rebound of the plates is going to create isostatic sea level changes, local sea level changes. So here is again Antarctic bed, the grounding line that used to be here. Because of the retrograde slope, there is potential for acceleration. So you can see that this flow here is accelerating down as the grounding line retreats. This flow is going to accelerate as well. Okay, so this is just showing other complications involved. I won't go into the details, but as westerlies shift south and circumpolar current is strengthening, a paper again came out just this week in Nature Communications from the Scripps group with Lynn Talley and so on, which shows that circumpolar current is accelerating. So that is going to create changes in sea level, summer ice reduction, shifts in the range and population of the penguins. Vegetation cover is going to expand when the land gets exposed. Human presence is already increasing because this is a geopolitically important place. Every country, including India, is putting camps there, permanent camps, maintaining personnel, spending a lot of money to keep that going. Increase in accumulation and snow can happen at high elevations because of warm waters, increased water vapor in the atmosphere, orographic precipitation, snowfall. Accelerating ice flow and mass loss is happening. Ground line is retreating. Basal melting is happening. That acts as an accelerator, as a lubricant at the bottom. This is more warm water intrusion as the ice shelf and the grounding lines retreat. So poleward migration of warm deep water is happening, and you will have effects in temperature, salinity, oxygen, acidification. So pH drops, acidification happens, oxygen drops, you're going to create anoxia, hypoxia, and you can see that near the surface as well. Okay, so just to show again, observed RCP 2.6, 4.5 and 8.5 projections are disheartening. If you've seen the movie Day After Tomorrow, then you know that warm waters here are reported first, and then New York City freezes over. And in the past, such things have happened where glacier melt theoretically can put a lot of fresh water on the Labrador Sea and Greenland, Iceland, Norwegian Sea, which can affect the Atlantic meridional overturning circulation. Remember, in the trends, we saw that there was a local lack of warming or cooling in this region. That can, in theory, increase the glacier mass, but we are not really expecting that to happen under the current warming scenarios. So this podcast is a little bit long, but it's okay because these processes of warming impacts on the Arctic, on glaciated regions, specifically on Greenland and Antarctica, and the differences in the processes of ocean, atmosphere, glacier interactions over Greenland and Antarctica are very key to understand how future will evolve. And we have already seen the impacts of such glacier losses on sea level, so we have to watch out for all these things, including acidification and oxygen deoxygenation and so on.